Question 1. A radioactive sample has a half-life of 6 days. How long will it take for 75% of a pure sample of the material to decay? At T equals 0, it's got 100% of the pure substance. And after 6 days, that goes down to half of that, so it goes down to 50% of the substance, and that's at T equals 6. After another 6 days, that goes down to a quarter of what it was. That's T equals 12 days. But the question says, how long will it take for 75% of the sample to decay? Even though we've got 25% of the sample left, that means that 75% has decayed. So our answer is 12. C. Question 2. A nucleus of platinum undergoes alpha decay to form an osmium nucleus as represented by the following reaction. What are the number of protons and the number of neutrons in the osmium nucleus? We know an alpha particle is 4 to He, which means that the proton number of osmium must be 78 minus 2, which is 76, because 76 plus 2 equals 78. We also can see that 175 and the platinum must go down to 171 for the mass number. That is the number of protons and neutrons. We know that we have 76 protons, so it's either B or D. How many neutrons do we have? Well, we have 171 minus 76, which gives us an answer of 95. The answer is D. Question 3. A student measures the count rate of a radioactive sample with time in a laboratory. The background count in the laboratory is 30 counts per second. What is the time at which the student measures a count rate of 45 counts per second? The first thing we do is remove background count from our counts. So we're looking at 120 there and 60 there. That tells us that 60 is directly half of 120, so the half-life is equal to 20 seconds. Great. Now let's go from 120, which is the original count, and let's do some movement down the half-lives. So it goes from 120 to 60, and that takes 20 seconds. It goes 60 down to 30, and that takes another 20 seconds, so we're up to 40 seconds. And then it goes 30 down to 15, which takes another 20 seconds, and that's 60 seconds. For each of those readings, we've actually taken the background count out, so what they're actually going to be is 150, 90, 60, and 45. Our answer's here. This is the answer on what the count rate will be to get us to 45, and that takes us 60 seconds, so the answer is C. A nucleus of krypton decays to a nucleus of bromine according to the equation. We've got krypton with 36 protons, and that decays down to bromine with 35 protons. That means on this side we need something to add up the protons so that each side has 36 protons. And the only thing that would add up the protons is a positron, and also keeps the mass number of the nucleons the same. So we're looking for a positron as Y. When you lose a positron, that's beta plus decay, you also lose a neutrino, not an antineutrino, so our answer is A. Question 5. Which development in physics constituted a paradigm shift? You'll know from TOK that a paradigm shift is a fundamental shift in the way that society thinks, or the way that you view something really important. And I'm going to go through each of the options here. A. The classification of variables into scalars and vectors. Okay, I'm okay with that, maybe. B. The determination of velocity of light in different media. No, that's just an experiment, that's not a paradigm shift. C. The equivalence of F equals ma to F equals the change of momentum over time. Nope, that's just the start of Newton's second law, that's not a paradigm shift. And D. The equivalence of mass and energy. Yes. When Einstein came up with the equivalence of mass and energy, it fundamentally shook the world of physics, and D is our answer here. Question 6. Outline by reference to nuclear binding energy why the mass of a nucleus is less than the sum of the masses of its constituent nucleons. That will bring you back to this diagram we had in step 1, and it was an imaginary scale. And if we put the mass of the nucleus on one side, when they're all bound together, it actually weighed less than the sum of the constituent parts. And that mass defect was explained by Einstein as a mass energy equivalence. So to answer the question of why the mass of this nucleus is less than the sum of its constituent parts, we have to mention the mass defect and its equivalence to energy. According to Einstein, the mass defect was equivalent to energy by this equation. And now what we have to do is explain where that energy is used up. This energy is binding energy, which is released when the nucleons come together. And then we should write this explains the mass defect. Polonium-210 decays by alpha emission into lead-206. The following data are available. Calculate in MeV the energy released in this decay. Whenever we see MeV, we know this question is going to be relatively easy. What's happening is that polonium-210 decays, releasing an alpha particle and a more stable product of lead-206. First of all, let's calculate the mass defect. We're going to calculate that in U, which is atomic mass units, and it's going to be the mass of polonium minus the mass of alpha and lead. That gives us a value of 0.0058 U. We know, and you've got to memorise this, it's not in the data booklet, that 1 U is equivalent to 931 mega electron volts. Therefore, if we do 0.0058 U times 931 mega electron volts, that will give us an answer of 5.4 mega electron volts. Just so you know, I tend to use 931.5 mega electron volts. It's just more accurate, but you can get away with 931. Whatever is easiest for you to remember. C. In the decay of polonium-210, alpha emission can be found by the emission of a gamma photon. State and explain whether the alpha particle or gamma photon will cause greater ionisation in the surrounding material. Remember that an alpha particle is a helium nucleus and it's actually 2+ charged. A gamma ray is an electromagnetic wave. There's no charge. That means that this alpha particle will interact with electrons surrounding it because it wants to attract the electrons towards it. Whilst gamma is high energy, it's not highly ionising. You can pop that into an answer if you like, but the answer is alpha for 1 mark. And the reason it is alpha is because it wants to attract the electrons or interact with the electrons. Question 7. 3 statements about radioactive decay are: the rate of decay is exponential. Yep. It is unaffected by temperature and pressure. Yep. The decay of individual nuclei cannot be predicted. Yep. Which statements are correct? All 3. The answer is D. Question 8. The background count in a laboratory is 20 counts per second. The initial observed count rate of a pure sample of nitrogen-13 in this laboratory is 180 counts per second. The half-life of nitrogen-13 is 10 minutes. What is the expected count rate of the sample after 30 minutes? The first thing we do is remove the background count. So we're going to start with 160. That's at t equals 0. After 10 minutes, it's going to be 80 because it's half of what it was. After 20 minutes, which is another half-life, it's going to be 40. And after another 10 minutes, which is 30 minutes, and that's where we want to be, the count rate will be 20. However, we have to add on the background count again. So at that point, our answer is 40. C. 9. 238 uranium undergoes an alpha decay, followed by a beta minus decay. What is the number of protons and neutrons in the resulting nuclide? 238, 92 uranium. Let's lose an alpha particle from that. That's 234, 90. And I don't know what that is, so we'll just change it like that. Plus 42He. And then this X particle loses a beta particle, and it's a beta minus particle. It looks like this. What adds up on that bottom? 91? Yep. 91 minus 1 gives us 90, and it gives us 2, 3, 4. So there's 91 protons. And remember, the number of neutrons is 234 minus 91, which is 143. So we've got 91 protons, 143 neutrons. The answer is 9C. Question 10. What statement is not true about radioactive decay? A. The percentage of radioactive nuclei of an isotope in a sample of that isotope after 7 half-lives is smaller than 1%. I can't really do the maths on that just now, so let's just wait and see if any of them are obviously not true. The half-life of a radioactive isotope is the time taken for half the nuclei in the sample to decay. That's true. The whole life of a radioactive isotope is the time taken for all the nuclei. No, I've never heard of whole life before. That doesn't make any sense. And D, the half-life of the radioactive isotopes range between extremely short intervals to thousands of millions of years. That's true. Now, if you are a student and you're like, never heard of whole life, but it could be a thing, let's just check and see if A is correct. One whole thing goes down to a half, goes down to fourth, goes down to eighth, to 16th, to 1, 3, 32th, 1 to 1, 64th, down to 1 to 8. 7 half-lives, isn't it? 1, 2, 3, 4, 5, 6, 7. So after 7 half-lives, that's the proportion of the isotope that's left. And you can tell that that's less than 1%, because 1% would be 1 over 100. So 1 over 128 must be less than 1%. So that is correct. Our wrong answer is C. Question 11. The age of the Earth is about 4.5 times 10 to the 9 years. What area of physics provides experimental evidence for this? Well, given that we're doing a radioactive topic, the answer is pretty clear. But if you didn't, but if we weren't doing a radioactive topic, you would be looking at these and thinking, well, how would optics, Newtonian mechanics and electromagnetism help us? The only possible one might be electromagnetism in terms of the Earth's magnetic field, but the rest of them are pretty useless. Also, we know that carbon-14 is an absolutely fantastic radioactive isotope for dating. And by dating, I don't mean hanging out with some cute person in your class. Not that kind of dating, because carbon-14 is pretty rubbish for conventional dating. It's very good for carbon dating, which is much less exciting. 12. An experiment is carried out to determine the count rate corrected for background radiation when different thicknesses of copper are placed between a radioactive source and a detector. The graph shows the variation of corrected count with the copper thickness. A. Outline how the count rate was corrected for background radiation. Well, what they do first is they take a reading with no source there, and then they subtract that from the count rate. A reading is taken with no source. I'm going to put this identifies the background count rate. Then the second point would be this rate is subtracted from the count rate. Now, I'm aware I wrote too much there, and the reason I wrote too much there is because I don't think we actually discussed that in step 1. So I'm just informing you how you would correct for the count rate here in step 2. But if you were looking at the exam technique, which we technically should be right now, all you'd really want is subtracted. B. When a single piece of thin copper is placed between the source and detector, the count rate is 110 counts per minute. The foil is replaced with one that is 3 times the thickness. Estimate the new count rate. What we need to do is we need to find the thickness that gives a count rate of 810 counts per minute, and then triple that thickness. So we go up to the graph, we draw a line across 810. Each of these little boxes is 40, so we're going really close to this line. And then we bring it down to find the thickness. And that looks exactly halfway between 0.5, so we're going to say the thickness is 0.25. Then we want to go 3 times that thickness to 0.75. All the way up and then across. It's tempting to say 400, isn't it? But actually, if you look really closely on the line there, the line crosses slightly below 400. I'm going to go with 390. It's not quite 400. 390, and we want to put our units. Counts per minute. C. Further results were obtained in this experiment with copper and lead absorbers. We've got a copper absorber at 3.5 millimeters thickness, and we have a corrected count rate, and then lead at the same thickness, which is less of a count rate. Comment on the radiation detected from this source. We know that alpha is definitely not going to get through copper or lead, and in fact, it's unlikely to even reach the absorber. So our first point is the radiation is not alpha. And we'll put 2 points with it. It is easily absorbed by thin paper and doesn't travel far. Given that there is radiation detected after lead, we have to assume it's gamma. We're going to say that gamma can travel through copper and is absorbed by thick lead. However, the thickness of lead there suggests that gamma will get through it. And finally, I think we want to address beta. In theory, beta could probably go through a thin metal, so it probably could go through the copper, but not the lead. And I just want to put one final sentence. If one radiation is present, then it's gamma. D. Another radioactive source consists of a nuclide of cesium that decays to barium. Write down the reaction for this decay. Cesium decays to barium, so 13755 cesium goes to 13756 barium. To make the proton numbers add up on each side, we need to have a -1 here, which tells us it's an electron, which tells us it's beta minus decay, which means we need to have that anti-neutrino on the end. Question 13. A pure sample of radioactive nuclide X decays into a stable nuclide Y. What is the number of atoms after 2 half-lives? Let's look at X and Y. At the beginning, X has 1 whole amount of this substance and Y has none. After 1 half-life, X has half and Y has half. After 2 half-lives, X has 1/4 of the substance and Y has 3/4 of the substance. That's 2 half-lives. The number of Y atoms over the number of X atoms gives us, do a bit of maths here, 12 over 4, which gives us 3. The answer is C. Question 14. The mass of a nucleus of iron is M. What is the mass defect of the nucleus of iron? Do you remember our imaginary scales that we had in the notes? And we said if we take the constituents of a nucleus on one side and place the nucleus on the other side, there's a mass defect. And in fact, the constituents are heavier than the nucleus. And that mass defect was the mass of this subtract the mass of that. And that's what we want to do here. We want to take the mass of 26 protons and the mass of 30 neutrons and then subtract this. So our answer is looking for subtract M. So it's that or that. These are out. And this is the answer here. 15A1. State what is meant by the binding energy of a nucleus. This is a definition. Just memorise it. It's an easy mark. It is the energy needed to completely separate the nucleons of a nucleus. A2. Draw on the axis a graph to show the variation with nucleon number of the binding energy per nucleon. Numbers are not required on the vertical axis. This is the graph that we've been waiting for. We know this graph. It starts from 0 and increases steeply to begin with. There's a little spike for helium, and at around about 56 we reach a peak. It goes like this. And then it sort of tails off, and it's roughly constant but goes down a little bit. Oh, I love that. That's perfect. E.3, identify with a cross on the graph the region of greatest stability. Great, we've already done that. And that's 56 Fe. Plutonium-238 decays by alpha decay into uranium. The following data are available for binding energies per nucleon. Show that the energy released in this decay is about 6 MeV. Our decay equation then looks like this. 238 plutonium goes to 42 helium plus 234 uranium. We know that helium, or the alpha particle, is 42 helium, and then we've just worked out that this is 234. There's also going to be energy, and it's this energy we want to find out. So we'll do 238 times 7.568 minus 4 times 7.074 minus 234 times 7.6, which gives us an answer of minus 5.51 MeV. We ignore that minus, that's fine, that's just giving us an amount of energy released in the equation. And is that about 6? Yes, well, if we take it to one significant figure, then that is 6 MeV. Question 16. 3 particles are produced when the nuclide 23 magnesium undergoes beta plus decay. What are 2 of these particles? Let's just do the equation. Mg goes to, we've got a +1 and 0, that's our beta particle. That means that to make everything add up, this has to be 11, 23, whatever that is. And it's beta plus, it's a positron, so we have a neutrino, which is not an antineutrino. Perfect. So we want the neutrino, and this 2311, the answer is A. Question 17. When a high energy alpha particle collides with a beryllium-9 nucleus, a nucleus of carbon may be produced. What are the products of this reaction? Oh, good. This gives us the opportunity to test our nuclear balanced equations. We have a alpha particle with beryllium-9, and we produce a carbon-6 and something else. Let's have a look. Right, well, on this side, we've got 13 nucleons, and carbon-12 is that. So we need to have something else that has a nucleon number but no proton number, which is a neutron. So we've got carbon-12 produced, and a neutron. The answer is B. Question 18. Which graph shows the variation of activity with time for a radioactive nuclide? Well, activity always crosses the y-axis with an initial activity. So that leaves out B and A. We know that it's either C or D. Due to the sheer scale of the number of nuclei inside a sample, it's very unlikely you'll ever see the curve go exactly down so the activity equals 0. There will always be some nuclei that are undergoing decay. Our answer is D. Question 19. What statement about alpha particles, beta particles and gamma radiation is true? A. Gamma radiation always travels faster than beta particles in a vacuum. Well, yeah, that's true. Gamma radiation travels at the speed of light, which is 3 times 10 to the 8 meters per second. And beta particles have mass, they can't travel as fast as that. A is correct, but let's just check that the rest are incorrect. B. In air, beta particles produce more ions per unit length travelled than alpha particles. Well, no, alpha particles have a charge of 2+, beta particles have a charge of 1-, and 2+ is more ionising than 1-. Not correct. C. Alpha particles are always emitted when beta particles are emitted. Nope, that's not true. D. Alpha particles are deflected in the same direction as beta particles in a magnetic field. That's not true because beta particles have a minus charge, alpha particles have a positive charge, and that means they would be deflected in different directions. The answer is A. Question 20. X is a radioactive nuclide that decays to a stable nuclide. The activity of X falls to 1/16th of its original value in 32 seconds. What is the half-life of X? Let's take nuclide X and say it's got one whole fraction at time equals naught. And let's see how many half-lives we have to do until we get to 1/16th. Great. There are 1, 2, 3, 4 half-lives to get to 1/16th. And those 4 half-lives happen over a span of 32 seconds. So 32 divided by 4 gives us 8. The answer is 8. Question 21a. Radioactive decay is said to be random and spontaneous. Outline what is meant by each of these terms. Random means you do not know which nucleus will decay, or cannot predict is probably a better way of saying it. And spontaneous means you can't predict when it will decay. There's a subtle difference that random means which nucleus will decay and spontaneous means when a nucleus will decay. That's a really easy 2 mark. A stationary nucleus of uranium-238 undergoes alpha decay to form thorium-234. The following data are available. And we've got data here. Calculate the binding energy per nucleon for uranium-238. So we've got uranium-238 decays to an alpha particle and 234 thorium. Oh, and we know that the energy released in the decay is 4.27 MeV. Great. That means that the energy of these, subtract the energy released, will give us the energy of the uranium. And we should of course note that all the energy given for each of these two is per nucleon. Let's do it. There are 4 nucleons in an alpha particle. So we have to do 4 times 7.07. Plus there are 234 nucleons in thorium. So we have to do 234 times 7.6. Take away 4.27. And that gives us 1802 mega electron volts. But that's for the whole of the uranium nucleus. We then have to divide it by the number of nucleons. So 1802 divided by 238 gives us an answer of 7.57 mega electron volts. Question 22. Which property of a nuclide does not change as a result of beta decay? You'll remember for beta minus, a neutron turns into a proton and releases an electron. For beta plus, a proton turns into a neutron and releases a positron. Either way, that's a neutron and it turns into a proton. That's a proton and turns into a neutron. There's the same amount of nucleons. So the nucleon number doesn't change. Question 23. The rest mass for the helium isotope is m. Which expression gives the binding energy per nucleon? Right, well the energy is equal to mc squared. And this m is the mass defect. The mass defect stems from the fact that the constituent parts of the nucleus are greater than the nucleus itself, meaning that some of the mass is turned into energy. With that in mind, the constituent parts of this helium isotope is, we've got 2 protons plus 1 neutron. Therefore, the mass defect must be that minus the mass of the neutron itself. So let's pop that into this equation. Delta E is equal to mp plus mn minus m times c squared. That's the binding energy of the whole nucleus. We want it per nucleon. So we have to divide by the number of nucleons, which is 3. And that's our answer there. The answer is B.